Hello, welcome to another module in this massive open online course. So, we are looking at the example problems to better understand the preliminaries required for optimization. Alright. In this module, let us start looking at another important concept, that is the null space of a matrix. Okay. So, what we want to understand as part of our examples for the mathematical preliminaries is this concept of what is known as the null space of a matrix. Now, what do we mean by the null space of a matrix? Now, consider a matrix A that is an M cross N matrix, then the null space of A denoted by this symbol N of A, this denotes the null space of A. This comprises of all vectors x bar. The null space of A comprises of x bar such that A x bar equal to 0, that is all set of all vectors A x bar such that A x bar, that is when multiplied by A x bar equals 0. Alright. So, that is basically that set. Alright. In fact, it is a space, that space of all vectors x bar is called the null space of the matrix A. In fact, this is a space, a vector space. You can see this as follows: if x bar, so observe that this is a vector space. This can be seen as follows: if x1 bar belongs to the null space of A, x2 bar belongs to the null space of A, then if you perform any linear combination alpha x1 bar beta x2 bar, then A times alpha x1 bar plus beta x2 bar equals alpha times A x1 bar plus beta times A x2 bar. But remember, x1 bar and x2 bar are both elements of the null space. So, A x1 bar, A2 bar is 0, which means this is alpha times 0 plus beta times 0, which is 0, and this implies that alpha x1 bar plus beta x2 bar also belongs to the null space of A, which means that the null space of A indeed is a vector space. That is because if x1 bar belongs to, what is the definition of vector space? If x1 bar belongs to the vector space, x2 bar belongs to the vector space, then any linear combination of these vectors must also belong to that set, that is known as a space or a subspace, a vector space or a vector subspace. Okay. Alright. And therefore, the null set, that is a set of all vectors x bar such that A x bar equals 0, is also a vector space, because if you take any two vectors belonging to this set, their linear combination also belongs to the set. Also, this is known as the null space. This vector subspace is known as the null space. Okay. Now, example, let us find, for instance, let us consider an example. Within this example, there is example number, this null space, this is example number 3 that we are looking at. Example number 3. Okay. And for instance, let us consider a matrix A that is equal to minus 1, 1, 2, 4, 2, 0, minus 1, 7, and what we want to do, so this is a 2 cross 4 matrix, belongs to the set of 2 cross 4 real matrices, and what we want to do is we want to find the null space of this matrix. Find the null space of this matrix A, and this can be found as follows. So, we want to find the set of all vectors, remember minus 1, 1, 2. So, we want to find the set of all vectors such that A x bar equals 0, which is minus 1, 1, 2, 4 into 2, 0, 1, minus 7 times well, remember, so 2 cross 4 matrix, so you have to multiply this by a 4 dimensional vector x2, x3, x4 equals 0. This is your x bar. Okay. What we will do now is we will perform row operations on the matrix A. Perform row operations on the matrix A. So, we have 1, minus 1, minus 2, minus 4, 2, 0, minus 1 or 2, 0, 1, minus 7. First, what we are going to do is we are going to perform reduce the pivot to 1. I am sorry. So, 1, sorry, this is minus 1, 1, 2, 4. Minus 1, 1, 2, 4, 2, 0, 1, minus 1. So, first we will divide R1 goes to R1 divided by minus 1. So, this will become equivalently, this will equivalently become well, when you divide by minus 1, this becomes 1, minus 1, minus 2, minus 4, 2, 0, minus 1, 7. Now, what we are going to do is we are going to perform R2 minus twice R1, the row operation. This will become the matrix, this will, first row will remain as it is, minus 1, minus 2, minus 4, 2 minus 2, 0, this will be 2, this will be 5, minus 1, this will be minus 1, minus 4, this will be basically you can see that this will be 2 R2 minus 2 R1. I am sorry, this is 2, 0, 1 minus 7. So, 2, 0, 1 minus 7. So, 1 plus 4, this will be 5, and minus 7 plus minus 7 plus 8, this will be 1. So, this is what you get. And now, what you can show, this is the equivalent matrix after row operations, and what you can show is that finding the null space of this matrix is equivalent to finding the null space of this row reduced matrix. This is equivalent to finding null space of the row reduced. Y is equivalent to finding the null space of the row reduced matrix. So, we will find the null space of this matrix, which we can find as follows. This will be, well, 1, minus 1, minus 2 minus 4 0 2 5 1 into x1 x2 x3 x4, this is equal to 0. This implies that well, we get two equations, x1 minus x2 minus 2x3 minus 4x4 equal to 0, and the second equation will be twice x2 plus 5x3 plus x4 equal to 0. So, we have two equations, 4 unknowns. So, observe here we have two equations, 4 unknowns, 4 unknown variables x1, x2, x3, x4. So, what this means is basically we have two free variables. We can set two of the unknown variables or two of the unknown parameters as free variables. So, let us set x3, x4 as free variables, and we will express the rest of them x1, x2 in terms of x3 and x4. Okay. So, set x1, x2 or x3, x4 as free variables, express x1, x2 in terms of x3, x4. So, we have, well, we have from the last equation we have 2x3 or 2x2 plus 5x3 plus x4 equal to 0. This implies that well, x2 equals minus 5 by 2 x3 minus half x4, and finally from the first equation we have x1 minus x2 minus 2 x3 minus 4 x4 equal to 0, which implies, if you can look at this, is that x1 equals x2 plus 2x3 plus 4x4. Now, substitute for x2, that is minus 5 by 2 x3 minus half x4 plus 2x3 plus 4x4, which is basically, now you can see 2 minus 5 by 2, that is minus half x3 plus 4 minus half, that is 7 by 2 x4. Okay. And therefore, the general structure of a vector belonging to null space of x bar will be of the form, well, minus half x1 is minus half x3 plus 7 by 2 x4, x2 is minus 5 by 2 x3 minus half x4, and this is x3 and x4. This is the, so this is the general structure. Remember, this is the general structure, or you can say the general expression of vector x bar belonging to null space of the matrix A. That is, if you choose any two parameters x3 and x4, I can form a vector like this x bar, which has this structure, all right, and that vector x bar will belong to the null space of this matrix A. So, this is the general structure or the general expression for any vector x bar that belongs to the null space of the matrix A. Okay. Let us try to simplify this a little bit further. So, we have x bar equals, now what I am going to do is I am going to write this as the sum of two components x3 times the vector, I can write this as, look at this, x3 times the vector minus half minus 5 by 2 1 0 plus x4 times the vector 7 by 2, x4 times the vector 7 by 2 minus half 0 1. So, I am writing this as the vector x3 times u1 bar x4 times u2 bar, that is, this is equal to x3 times observe this is a linear combination of u1 bar and u2 bar. This is a linear combination of the two vectors u1 bar and u2 bar. Therefore, any linear combination of these vectors u1 bar and u2 bar belongs to the null space of A. Alright. So, this null space of A is formed by all linear combinations of these vectors u1 bar and u2 bar, and therefore, these u1 bar and u2 bar are the basis vectors for the null space of the matrix A. So, what are these vectors u1 bar? You can clearly see u1 bar equals the vector minus half minus 5 by 2 1 0, this is the vector u1 bar, u2 bar is the vector minus 7 by 2 minus half 0 1. So, these vectors are basis vectors. Okay. So, what we are saying is that these vectors, these are basis vectors for the null space of A. That is, the null space of A is formed by the all possible linear combinations of these vectors u1 bar and u2 bar. In fact, you can quickly verify that u1 bar, u2 bar themselves belong to the null space. For instance, if you consider A u1 bar, now also remember u1 bar comma u2 bar themselves belong to the null space of A. You can quickly check this. For instance, A times u1 bar equals, multiply this, minus 1 1 2 comma 4 2 0 1 comma minus 7 times, if you look at this, minus half u1 bar minus 5 by 2 1 0, this is equal to, what will this be equal to? This will be equal to, well, the first row will be half minus 5 by 2 plus 2 plus 0, second will be minus 1 plus 0 plus 1 plus 0, and you can clearly see this is nothing but the 0 vectors. So, this implies AU1 bar equal to 0. They form the basis. Naturally, u1 bar and u2 bar itself in that space. Similarly, AU2 bar equals 0. You can check that. Similarly, AU2 bar is also 0. Alright. So, that is a concept of the null space of a matrix, that is the set of the space of all vectors x bar such that Ax bar equal to 0, and we justified that this is actually a vector space, because if you take any two vectors belonging to this space, the linear combination also lies in this space. Okay. Let us look at another example, example number 4, and this is regarding the trace property. This is regarding the trace of a matrix. Remember, let briefly just recall the trace of any matrix is defined only for a square matrix. This is defined and trace of a matrix, remember, is the sum of the diagonal elements. So, if A is an n cross n square matrix, trace of A is basically the sum of the that is trace of A is nothing but the, that is, if A equal to this matrix, this is an n cross n matrix, the trace of the matrix equals the sum of the diagonal elements. Trace of the matrix is sum of the diagonal elements. So, trace of A equals A11 plus A22 plus so on, that is basically, if you look at this, I equals 1 to n AII, and that can also be denoted as summation I equals 1 to n, take the element A I. This denotes basically I comma I element of A. This notation basically denotes the I comma I element of the matrix. So, the trace of a square matrix A is basically the sum of the diagonal elements of the matrix A, alright, A11 plus A22, A33 plus A33 and so on. Okay. Now, if you look at now the property that we are interested in proving, I have not got to the property, that problem that we want to prove. We want to show that for any two matrices, let us consider two matrices, A of the same size, A belongs to M cross N, and B not same size, but B belongs to N cross M. So, A transpose and B have the same size rather. So, A is M cross N and B is N cross M. So, basically, so that we can multiply A and B, then we can show that trace of AB equals trace of BA. This is an interesting property. So, we want to show that for two matrices A which are of size M cross N and N cross N, trace of AB, that is sum of diagonal elements of AB, is same as the sum of diagonal elements of BA. Now, note, this does not imply that AB equals BA. One should not confuse that simply trace of AB equals trace of BA does not imply that AB themselves AB itself is equal to BA. In fact, AB in most general AB typically is not equal to, because if you look at AB is of size M cross M, BA is of size N cross N. So, the matrices, if M is not equal to N, the sizes themselves are different. So, AB is not equal to BA. So, look at this, this is M cross N, this is N cross, this is an N cross N matrix BA. Okay. Now, let us start with this proof, and this is a very interesting property. So, and this is very helpful in several simplifications. Now, first let us start by looking at the ijth element of the matrix product AB ij. You can show this is equal to summation k equals 1 to n of aik bkj, that is the ijth element of the product is summation of all elements in the kth row of A and jth column multiplied by corresponding elements in the jth column. So, this basically is kth row of all elements in the kth row of A, and these are elements in the that is you take the kth row of A, jth column of B, I am sorry, this is jth column of B, okay, and do an element by element multiplication and then take the sum, that is the ijth element of AB. Now what is ABII? That is the diagonal element. Diagonal element is simply take the ith row of kth row, this is simply, I am sorry, this is the ith row of A, k equals 1 to n, this is simply A I comma k into B k comma I, because we are looking at the ith element. So, this is ith row of A, ith column of B, okay. And now trace of AB, recall trace of AB is nothing but the sum of the diagonal elements. So, that is basically you have to take the summation over I equals m of all the diagonal elements ABII, correct. This is the sum of the diagonal elements, which is equal to, now substitute this expression for ABII, that is summation I equal to m, summation k equal to 1, A ik bki. Now what I am going to do is I am just going to write it in a different this product. So, I equals 1 to m, summation k equals 1 to n. Now I am going to first write bki, aik bki is bki times aik. So, I am going to write bki aik. Now I am going to interchange the summation, the order of summation. So, I am going to interchange the order of summation, that becomes k equal to 1 to n, summation I equals 1 to m. Now I have bki aik. Now look at this bki is basically nothing but, this is basically kth row of B, kth row of, and aik is correspondingly the kth column you are taking an element wise product of kth elements of kth row of B and kth column of A. So, this is nothing but the, if you look at this, this is nothing but the kth element of BA. So, if you look at this, this is nothing but you are taking BA, kth row and kth column, and this is basically kth element of Bk, and therefore, what you can see is basically this is summation I equals 1 to m, you take the matrix product BA and this is the kth, which is the diagonal kth diagonal element of Bk, and you are taking the sum over all the, I am sorry, sum over k equal to 1 to n, you are taking over the sum of all the diagonal elements k equal to 1 to n BA kk, which is nothing but trace of BA. So, this is nothing but the trace of BA, correct. This is nothing but the trace of BA, and therefore, what we have is trace AB, and this is very handy property, trace AB equals trace of trace AB equals trace of BA, and this is very handy property because in general for matrices you do not have a commutative property, that is AB is not generally equal to BA, but trace of AB equals trace of the matrix BA. This is an interesting property of matrices which will come handy in several problems or several optimization problems where you have to manipulate matrices or manipulate the product of matrices, alright. So let us stop here and we will continue with some other problems in the subsequent modules. Thank you very much.